All right. So this is stuff you should be familiar with. Hopefully you studied hard in 1010 and 1050, because I think most of you had those classes. And hopefully you got done with 2.1. We were talking about like the fundamental shape of a sine graph and a cosine graph. There were 5 key points that you need to know on each one of them. We were going to work on graphing the beginning, the middle, the end, and then the quarters. It's a really important skill to have. And this section starts out with a starter question. It says, can you describe why this graph would be moved left 1 unit, while that one is moved up 1 unit? So they're both the same parent graph, the regular old parabola. This one moves it to the left 1 unit, and this one moves it up 1 unit. So can anybody, this one's the easier of the two. Can anybody explain this to us?
X and Y can stay the same, but the Y would more than what it would usually.
Okay, so for any number that you plug in to make the regular shape, all that happens to get the Y value is you just take that same answer and add 1. So this changes the Y values, right? That's why it moves it up 1. Can somebody explain to us why this moves it to the left? Greg?
It happens sooner or later on the graph, so like if it's negative, it's changing the X, moving it back down the X axis. So
Okay.
it changes the X before it becomes the Y axis.
Okay, changes the X before it comes to Y, or it changes the X before it makes the shape that it's supposed to make. Okay, so if the shape here is squaring, or made by squaring, so it's a parabola, okay, we make the shape and then we add 1 to it. That's just going to take the same shape and move it up 1. Okay, if we take the X and we change it before we make the shape, what this is going to do is it's going to make, as Greg said, it's going to make it either sooner or later. Okay, by adding 1, it makes the shape 1 unit sooner than it normally would. So if we normally come along here and we make a parabola that looks like this, we've changed this by adding 1 to all the X values. So -1 acts like a 0. So it makes it 1 unit sooner than it should have. Okay? So I think that's a decent explanation. So you're really familiar with transformations, we call them, if we're working with like parabolas and pretty simple graphs like that. So even if we put like a 3 in front of this, that still would be a pretty easy function to graph. That would vertically stretch it, and that would move it up 1. Okay, we could even we'll do some more complicated ones in just a second. But let's take a look at this. We actually had a diagram kind of like this last time when we talked about what each one of these things would do, except for one thing. What does that A do? Talked about it last time. What does it do to the shape of the graph? Okay, so it's a vertical stretch. Okay, in this particular case, we use an A kind of strategically. That's going to be the amplitude. Okay, using the vocabulary that we learned last time. The notes are right there. Okay, and if it's negative, okay, if it's negative, then it's going to be a vertical flip. Okay, this one's not bad. That one's pretty easy to describe. What does that do? Moves it up or down depending on whether D is positive or negative. So we call this a vertical shift. Okay, vertical shift there. We did talk about this one last time. What does that one do? Okay, it's a phase shift. It either shifts it to the right or to the left. Okay, so we call that a phase shift.
Why not a horizontal shift?
We can call it a horizontal shift. In fact, we called it a horizontal shift in 1010 and 1050. We call it a phase shift in trigonometry just because we talk about the phasing or the cycling of the graph. If we're going to shift that phasing, it's just a fancy word for it. Okay. Now, there's one thing you do have to remember about the phase shift. It does the opposite of what you'd think, just like this does. Okay, I suppose you could call that a phase shift. Okay, it moves it left when you'd think it moves it to the right, so it does the opposite. And then we're going to talk today I mean, we already know what those three things do. We're going to talk about what this one does. Okay, this one is called a period change factor. It's called a period change factor. Now, we're going to talk about why it's called that in just a second, and I completely made that phrase up because it describes what it does. Probably won't find that in any textbook. They would probably call it a horizontal stretch or shrink, but because all of the trig functions that we deal with have periods, I find it a lot easier and a lot more meaningful to just call it a period change factor. It's the factor by which we're going to change the period. So let's come down here and let's take a look at this. It says when we're changing a function to make a transformation, like the stuff that you're familiar with up here on a parabola, if a change is made to x before the function makes the shape, then it changes the x coordinates of the points on the original graph. So that's why this takes that same shape and moves it to the left. It changes the x coordinate, okay? And it does the opposite of what you would think that it does. So up here, if you just said, hey, what do you think adding 1 does to the x? You would think it just adds 1. You'd think it moves it to the right, but it doesn't. It moves it to the left, okay? So we've talked about what A, C, and D do, but now we're ready to talk about what B does to the shape of a sine and a cosine curve, okay? So if we've got these two shapes, which were both sinusoidal curves, they were just those wave functions that we talked about last time, what do you think y equals sine of 2x would make? So it looks a heck of a lot like this one. The only thing that's changed here is we've put a 2 in front of the x. So if we were to put parentheses around this, like we could, takes the angle that we plug in, doubles it, then we'd figure out what the sine ratio of that particular angle is. Okay? Well, one way we could figure this out for ourselves is we could say, well, does the 2 change the x before the function makes the shape? Or does it change it after it makes the shape? So think about what we talked about up here on these examples right here. Why do these do what they do? Squaring makes the shape. Are we changing it before we make the shape or after? Because if we change it before, like this one, which coordinate's going to change? The x coordinate, okay? So does changing the x before the function makes the shape, so that's going to change the x coordinate, or does it change it after it makes the shape, and that would change the y coordinate? So the big question is, does it change it before, or does it change it after? So take a good look at this. If you were to pick a number, an angle, and plug it in, what's the first thing you'd do with it? You'd multiply it by 2, and then you'd find the sine of that particular angle. So we're changing it before it makes the shape. We're going to change it in the x direction, in the horizontal direction. Okay? So, since we're multiplying by b, that's going to change the period. In other words, it's going to change the horizontal distance needed to repeat the shape. Okay? Remember, that's what the period was. Okay, so I've got a couple little formulas right here. This is why I call it the period change factor, because that's the only thing that number does. It just changes the period. So, in order to figure out what the new period is, take the old period and divide it by whatever that number is, whatever that period change factor is. So if it's 2, we're going to divide by 2. If it's an 8, we're going to divide by 8. Now, for the sine and for the cosine function, does anybody remember what the period was on those?
2 pi.
It was 2 pi. Okay? So, just for sine and for cosine. If you're graphing those, the old period is 2 pi, so all you have to do is take the old period, 2 pi, divided by the period change factor. That's going to be our new period. Okay? Any questions so far? Okay, those are all the ideas behind what we're going to cover today. Now we're just going to graph a bunch of these. Okay? Try and see if we can get this figured out. So it says graph y equals sine x using a dotted curve. So we're going to put a dotted parent function on here, if you will. And then we're going to graph this one using a solid one. So I'm going to do this in black. And remember, we marked the beginning, the middle, the end, and the quarters. So this is going to be 0. This is going to be 2 pi. This is going to be pi, pi halves, 3 pi halves. And remember, you want to be able to graph the 5 key points. So if you did this over the weekend, if you got done with 2.1, this is an absolute piece of cake. Because you know, when I say, where does sine start? Your answer needs to be, well, let's see, did sine start at 1 and go down, or did it start at 0 and go up? Which was it? Starts at 0 and goes up. So my first key point is here, then up to here, then to here, down to here, and back to here. So I'm going to connect these with a little dotted curve. So this is what the sine curve looks like. Again, this is just the parent graph. Looks something like that. That is the original shape. That's what sine of x looks like. Now we're going to graph this one. Now we're going to graph sine of 2x. So the only change that was made here, remember last Friday we were working on phase shifts and amplitude changes and all sorts of stuff like that. The only thing that 2 does to this graph is what? Changes the period. That's it. Okay? So this is a period change factor. It's going to change the period. In order to figure out what the new period is, we take the old period and we divide it by the period change factor. So in our case, the old period is 2 pi. We're going to divide that by, what is this? 2. So what's the period for this particular function? Pi. That's the new period. New period. Okay? So, did it slide it left, right, up, down, or anything like that? Nope. So this is still the beginning. It's still going to start right there. It's still going to have 5 key points. It's just going to do those 5 key points in different places. So we start right here. Where's it going to end? How far away? Pi, right? So over to here. That's the end. Where's the middle? Right here. Where's the first quarter? Right here. And the third quarter is right here. That is one cycle for this particular graph. So I'm going to draw this in a solid curve. Going to look something like that. Now I could continue this. Remember, this is a sinusoidal curve. It's going to repeat that pattern every pi units. So it's going to come up here and hit 1, come back down and hit 0, down here and hit -1, and like that. So if you would, go ahead and continue that. Graph the whole thing again. One more cycle. And there's no reason why we couldn't continue it on this side either. So it's going to go something like that. Any questions? Sure? Okay. So the black dotted one up on this, that's the original sine curve. That's sine of x. The red one is sine of 2x. Doesn't it look like this has been horizontally kind of squished, shrunk? It does. Okay? Victoria.
So did you go by pi-fourths?
Yeah, if we were to label these, which I haven't yet, okay, I just want to talk about this again for just a second. Remember, this is pi halves right here. So this point right here would be pi fourths.
So why would pi-fourths be on 1?
We'll answer that. Does everybody agree that this point right here, if I were to label it, is pi fourths comma 1? Okay, so the question is, why is that on the graph, right? Remember, a point can't be on the graph unless it works in the equation, right? So let's see. If I plug this into that function right here, what do I get out? So I'd get the sine of 2 times pi fourths. Well, what's 2 times pi fourths? Pi halves. What's the sine of pi halves? Sine of pi halves is 1. So did I get the right point? Okay, so if you kind of blend this, that's a perfectly good question. If you think about that with this question right here, why does y equals sine of 2x make the shape that it does? Why did it change this way? Why was it horizontally shrunk? Why did it compress it together?
Because it does the opposite of what you expected.
It does the opposite of what you'd think. So if I said I'm going to change this in the x direction and I'm going to times it by 2, you'd think it would horizontally stretch it, right? But it doesn't. We just got through saying that whenever you change the x, it does the opposite of what you'd think. So if you think it stretches out by 2, it doesn't. It shrinks it by a factor of 2. Or in other words, it shrinks it by half. 1/2. Reciprocal relationship there. Does that make sense? Can somebody think of another way? There's a way of thinking about 2 that would make more sense on this one. What does it do to the way it makes the shape? Yeah, Jeremy?
Put 2 sine waves into 1 sine wave.
That works. Take a look. It normally completes one cycle in 2 pi. How long did it take it to complete it now? Only pi, half the time. So it must have sped up the cycling. It must be cycling twice as fast. So if it does it twice as fast, it's going to complete a period in half the time. Does that make sense? If we put a 4 here, it would go 4 times faster, and the new period would be a fourth of what the old one was. Does that make sense? Okay, that's what's going on here. The 2 is speeding up the cycling. It's speeding up the shape, so it reduces the period. Does that make sense? Okay, so let's write that down. By multiplying by 2 speeds up the graph. It makes the shape twice as fast, so it completes a cycle in, what are we going to put there? Half the time. So the new period is half of the old period. Again, that's why these formulas, hopefully these will start to make sense as you use them a bit. That's why we're dividing by b rather than multiplying by b, because there's that reciprocal relationship. That's doing the opposite of what you'd think. Times it by 2, my gosh, I actually shrink the time by a half. Times it by 8, I shrink it by an eighth. Okay? Does that make sense? Okay, so let's take a look at the next one. Now, this one, for most people, this looks like a bit of a mess. This does not look like any fun to graph because it's got this, oh gosh, this is an ugly fraction. Pi fourths. My gosh, it's complicated enough that we have to plug in an angle that's in radians. Now we have to multiply it by something that's an ugly fraction like pi fourths. This actually makes this kind of nice. Now I want you to think about this for a second. The number pi fourths. Could you say approximately what that is? It's a number you've heard before. Will just be 3.14159 divided by 4. Throw that in a calculator, and what does it spit out? What is it? 0.7?
85398.
0.785. Okay? It's about 3/4. It's a little bit more than 3/4. Now, this number up here that we multiplied by, it was bigger than 1. So if I multiply by a number that's bigger than 1, you'd think it stretches it. It doesn't. It horizontally shrinks it. So what do you think this is going to do if we multiply by a number that's smaller than 1? Yeah, it's going to stretch it out. It's not going to speed it up. It's going to slow it down. It's going to slow the cycling down, so it's going to take longer to complete one cycle. Well, here's the cool thing. The new one equals the old one divided by b. So in our particular case, what's the regular period for a cosine graph? What's the old period? The normal period? 2 pi. So if I take 2 pi and I divide it by, what's my period change factor here? Pi over 4, right? Pi over 4. Well, that looks really ugly until I do this. This is a complex fraction. I'm going to flip it over. That's going to be 4 over pi. The pi's cancel. What's the period for this graph?
8.
Holy cow, that's a nice number. I can deal with that. That's better than dealing with pi's. So let's mark the beginning, mark out the end, the middle, eyeball the middle, and then eyeball the quarters. Now, if this one starts at 0 and its period is 8, where is this? 8. Where is this? 4. 2 and 6. Well, that's pretty nice. Now, did we do anything else? Did we do an amplitude change? Did we vertically stretch or shrink? Do we have a phase shift, a horizontal shift, or anything like that? Nope. The only thing we did with this was we changed the period. Okay? So that means it's, well, wait a minute just a second. So I'm going to ask this question again. I'll say this all the time over the next couple of chapters. Where does the cosine graph start? Starts at 1 and goes down. So we're going to start here. I'm going to put this as 1. There's my first key point. It goes down and hits 0. It continues going down and hits -1. Then it comes back up and hits 0, and it finishes off right back where it started at 0. So my graph looks something like this. And correct me if I'm wrong, but those would be pretty easy to label, wouldn't they? A lot easier than this one up here. Okay, any questions? Okay, would you label this point right here? Max, where is this point? I'm just giving you a hard time. It's at 6, 0, right? Okay. And this one right here? 4, -1. Okay. And let's come back up here. I need to know where this point is right here. If you did that practice in 2.1, there were a whole bunch of problems where it asked you to find the midpoint, slide this point left, right, all that sort of stuff. This is right in between pi halves and pi, so that's got to be 3 pi fourths. We didn't slide it up, down, left, right, or anything like that. This is still at -1. Okay, are there any questions? Okay, last thing on this page, and then we'll flip it over. Let's say we graphed the original one, the parent graph for cosine x. So y equals cosine x. That would start at 0, 1, and it would finish in 2 pi, or on our graph, not a very convenient point, about 6.28. So about right there. That's where it would finish. Pi would be about right here, a little more than 3, because 3 would be about right there. Okay. Pi halves is at about 1.5, so we're about there. And then this would be 4.71, I think, so somewhere about right there. So I'm going to draw those 5 points, and I'm going to sketch what the cosine graph normally looks like. And then I'm going to ask you to look at this for just a second. Does the green graph look like a horizontal stretch of the black dotted graph? Stretched out just a little bit, right? Slowed that cycling down just a tad. It normally gets done here. We're going to get done here. Okay, does that look okay? Can you see how this period, why I call it a period change factor? That's all that number does. It either speeds it up and shrinks the period, or it slows it down and stretches the period out. Okay, any questions? Okay, go ahead and flip the page over then. Got several graphs to do on this next page. Okay, now the first thing I'm going to warn you of is occasionally they're going to write things the wrong way. They're seeing if you're paying attention and you've got things straight. Now, I'm going to come back up here and I'm going to make a big deal of this. If you write them this way every single time, you're going to be in much better shape. You're going to get them right. But I guarantee, just like I predicted on the last test, I warned you about a common mistake people make, and there were still people that made this mistake on the test. So don't make this one on the test. A lot of people forget that this has to be in factored form. That is a plain old x. So if there's a number in front of the x, you better pull it out. Okay? If you just blindly look at this and say, oh, that's a 5, the phase shift is 5, or something like that, you're going to get it wrong. Okay? So this has to be in factored form in the middle there. Okay? So the other thing is, when they wrote this one, they wrote it backwards from the way they normally do. We normally don't see things like this. We normally just like writing the x squared, that shape first, and then add 2, so that we can see what the vertical shift is. So the first thing we're going to do with this is we're going to do this. We're going to write minus sine of x over 4, and then we're going to write plus 2. So we got a couple things going on here. So let's take a close look. What does that do to the graph? What does the negative do? Okay, so this is a vertical flip. What does the 2 do? It's a vertical shift, so I'm just going to write up 2. Okay, now, take a look at this guy right here. Did we change the x? Yes, we did, by quite a bit. By this number right here, the period change factor is... Okay, if you need to write it like this, if you need to write sine of 1/4, remember I said you can factor things out, write it as if it were a factor. The number that it's been multiplied by is 1/4. So my question for you is, before we even figure out what the period is this going to stretch it out by slowing it down, or is this going to speed it up and shrink it? It's going to stretch it out, because what does the 1/4 do? Slows down the cycling. So let's figure out what the new period is. So the new period is the old period, which is 2 pi, divided by the period change factor, 1/4. So that's going to be, let's see, I flipped that over, 4/1, so that's going to be 8 pi. Holy cow, the period is 8 pi. Okay, now, in this box here, this is a reminder of what we talked about on Friday. For most people, not everybody, but for most people, including myself, I find it a lot easier to make the shape and then move it where you need to. Make the right shape, then move it where you need to. Now, when we say make the right shape, what we're talking about is find out what the amplitude is, has it been vertically stretched or shrunk, and find out what the period is, has it been horizontally stretched or shrunk. Once you have those things, you've got your 5 key points that you're going to need to move. Okay? Any questions? Okay, now before I start graphing this on here, I'm going to think about this for just a second. This has been vertically flipped, and I'm going to have to move it up 2 units. So all I need to do is make sure I've got room to move it up 2. So here's what I'm going to do. I'm going to make the vertical scale big enough to fit that. We're going to come down here to 1. Now I'm going to graph the shape, the right shape first. Is everybody okay with that? So I'm going to start at 0, start right here, and then I'm going to mark the end. Okay, the end is at 8 pi. So this is 0, this is 8 pi. And then I eyeball the middle, and I eyeball the quarters. Now this looks like it's pretty awful, but it actually turns out to be pretty easy. Because this is 4 pi, 2 pi, 6 pi. Okay, it's a sine curve. Does it start at 0 and go up, or start at 1 and go down? Okay, starts at 0, right? So if we just kind of simplified it and said, where does it start? It starts at 0. So I'm going to put a point right here. Now, it's been vertically flipped, right? So it's not going to go up to 1, it's going to go down to -1. It's going to start by going down. So it's going to look like this. There's the first key point, there's the next one, and the next one. So there are the 5 key points. Now, if I were you, okay, when I'm drawing these, I've got the 5 key points. I have the correct shape. I have the correct amplitude. It starts by going down. It indicates it's been vertically flipped. And I have the right period. Starts at 0, ends at 8 pi. What I like to do is I just like to either just put those points, make sure they're clear. That's why I've made them nice and big and fat. And then I like to dot it in. Okay, that is the right shape that I have on the board right now. Now, once you've got the right shape, then you can just move it where you need to. Now, the only way we're going to move this is either left and right or up and down. And on this particular problem, what's the only thing I need to do to finish this problem off? I just need to move it up, right? How far do I need to move it up? 2. Now, if you need to label every one of these points before you move them, please do. Because the only thing we need to do is change which coordinate if we're moving it up? Just the y coordinate. So I like to just look at it and think for a second. Where is this point? This point is at 0, 0. I'm going to move it up 2 units. So I'm going to move it up here. This point is at, well, let's think for just a second. This point is at 2 pi -1. I need to move it up 2. So where's that going to put me? That's going to put me at +1 right here. Okay. Now, some of you have your heads down and it doesn't look like you're sleeping. I think you're working ahead. That's great. You know what you're doing. I need everybody to watch up here, please. This can be really helpful. If we know we're going to take this graph and we're going to move it up or down, if we know we've got a vertical shift, a lot of times it makes you a much better graph and makes it easier to figure out where those final points end up if you draw the midline, that center line. So the center line right now is the x-axis. I need to move everything up 2 units, so it can be helpful to make a nice sketch if you just draw in where the midline would be. Now, notice that this ended up in the right place. Notice that this one looks like it's about 1 unit below the midline, just like this was 1 unit below the midline. Where should this one be? Should be right on the midline, right? So I'm going to put this one here. Where should this one be in comparison with the midline? 1 above. Okay, if I count up 2, that is where I'm going to end up, and this one ends up right here. Those points are the 5 key points. I do need to label those and sketch the graph. So I'm going to sketch the graph. You sketch the graph, and please label those 5 key points. I'm going to put arrows on the end to indicate that that does continue in both directions. Yeah.
So you do multiply the y coordinate with 2, or you keep adding, right?
All we did was add.
Okay.
Yeah, it was just a vertical shift. All we did was add 2 to each y coordinate. Any questions? Okay, so this point here is 0, 2. This point is 2 pi comma 1. This point is 4 pi comma 2. Well, let's see, those all have the same y coordinates, so this is going to be 8 pi comma 2, and this is going to be 6 pi comma 3. Any questions there? Good, then just watch. Here's the original sine function. All this blue one is just a transformation on the sine curve. Here's what the original sine curve would look like on this scale. It would start here, it would end at 2 pi, and it would go up to 1, hit 0 on the way back down at pi, and then it would go down to -1. So here's the original one. Okay, now, look at the original one, and look at what we ended up with. Does it look like, first of all, vertically flipped? Instead of starting and going up, it starts and goes down. Does it look like it's been horizontally, look at that, stretched, slowed down by a factor of 4? It takes 4 times as long to make the same shape. And did we slide it up 2 units? We did. Okay? All right. Are there any questions? Okay, I've gone kind of slow for the most part. Everybody okay? Because I am going to speed it up just a tad. Okay, take a look at the next one then. Okay, I warned you about something a minute ago. What was it? And what can you see on this particular problem here? What?
The pi over 3 needs to be factored out.
Okay, the pi over 3 needs to be factored out. If you're going to get this right, somebody's going to make this mistake on the test. They're going to look at this and say, oh, I know what the period change factor is, and I know what the phase shift is. You don't. You have to rewrite it so it's in that factored form. So this is a cosine. Here's the period change factor. You can get that right by looking at it, but most people can't get the phase shift right. So the phase shift on this one is? Write down the phase shift, please. Phase shift is +1. It's going to move it to the right, isn't it? If we say the phase shift is +1, we know it's going to shift it to the right. If we say it's -pi4, we know it's going to shift it to the left pi4. Okay? Now we need a period. Changes it to 6. A little less than 2 pi, because 2 pi is 6.28. This is a horizontal shrink. It speeds it up just slightly. Pi3 is just a tad more than 1. Just barely more than 1. So again, the way you do that is you take the old one, for sine and cosine, the old period is 2 pi, divide by pi3. When I flip that over, the pi's are going to cancel. I'm going to get a 6. So I have a phase shift of 1, and I have a period of 6. Now, if I want to make the right shape, what 2 things did I say were involved in making the right shape? Amplitude and period. What's the amplitude on this graph? It's not a trick question. It's 1. It never changed. It's the same as the one on the parent graph. So the amplitude is 1 and the period is 6. So we're going to mark the end, the middle, and the quarters. This is 0. This is 6. This is 3. This is a little bit of a pain in the butt. This is 1.5 or 3/2. This is 4.5 or 9/2. Does everybody agree there? This is a cosine. It starts at 1, so it's going to start here, then down to here, up to here, and up to here. Okay, now, that is the correct shape. I have the correct shape. We could take the time to label each one of those points, but this is not the right graph. What have I not taken care of on this function to make the correct graph for this particular problem? Okay, I need to take all of those points, and what do I need to do with them? Move them to the right 1 unit. So let's think about where they are. Now, I don't need to redraw the midline because that's already there. Okay, we didn't slide it up or down. I need to take this point and I need to move it 1 unit over here. The minute we start messing with scales, like if this scale is not the same as how far we're moving it, gets to be a bit of a pain in the butt. I'm going to move all of these 1 unit to the right. This is the correct graph. I'm going to draw a nice solid curve for this one. All right, maybe it's not so nice, but it's solid. And then we need to label all 5 of those key points. Any questions? Where is this one? Very good. It's at 2.5, 0. Because it was at 1.5, 0. The only thing we had here was a phase shift of +1, so we move it to the right one, and there we go, 2.5, 0. This one would be at 1, 1. This one would be at 4, -1. Next one. 5.5, 0. Notice how all of those two have the same y coordinate. And then this one right here. Where is it? 7, 1. For 2 reasons. The old one used to be at 6, 1, so if I go over 1, that would put me at 7, 1. Good there? Or, where did it start? And how long does it take to complete 1 entire cycle? 6. So if it started at 1, 1, it better finish the cycle 6 units away horizontally, so at 7, 1. Any questions there? Okay. Let's take a look at, this is the last one, right? Almost the last one. Last one we have to graph. Okay, so this one has everything all together. Okay, this is a bit of a mess, but we can handle this. They don't get any more difficult than this. I am going to tell you this right now. If you can do this problem without making a mistake, you have at least one problem worth probably 10 points on the exam, all taken care of. We're also going to have a quiz in a couple days to make sure that you can graph stuff like this. And if you can do that, you're in great shape. This has all the stuff we need on it. What's wrong with this? It's not factored out. So here's what we want to do. We want to write this as -1/2. It is a sine curve. We want to factor this out. So that's going to be 3. X, let's see, if you factor out a 3, factoring out is the opposite of multiplying in, so it's like dividing out. So if you divide this by 3, what do you get? Pi6. And then -1. So this is all written correctly. Okay, we're in good shape on this one. Now we just need to identify what's going on here. That's a vertical flip, and it changes the amplitude, right? This moves it down. This moves it right. And what does this do? Horizontally shrinks it. It changes the period. It speeds it up by a factor of 3. Okay? All right. You ready? Okay. Here's what I'd need to identify first. Remember, you want to figure out what the amplitude is, and you want to figure out what the period is. Those two things determine the shape. I know what these other guys do. These are easy once I know what shape I've got. This is going to be moving the shape down 1. This is going to be a phase shift of, let's write it with the proper sign. Positive or negative? Positive. Positive pi6. So I know once I get the right shape, I'm going to be moving things to the right pi 6 and then down 1 unit. What's the amplitude? Half. Amplitude is a half. Okay? Remember, it's whatever this number is. You can ignore the sign. The amplitude is never negative, so don't put negative 1/2 here. Okay? And what's the period? What's the period? 2 pi divided by the period change factor, so it is 2 pi thirds. These two things are going to determine the shape. Once you know the amplitude is 1/2 and the period is 2 pi thirds, we're all set to go. Ready? Okay, keep in mind I need to move this graph down 1 unit, so we don't want to make the scale too big in the vertical direction. So I'm going to go, let's go 1, 2, 3 up here. Scale this one the same way, so it looks right. Yeah.
How'd you get 2 pi thirds for the period?
What's the regular period for a sine function? 2 pi. And then the formula is always take the old period divided by whatever the period change factor is. So our period is 2 pi, and the period change factor is a 3. It's that number right there. That's our b. So 2 pi divided by 3 is just 2 pi thirds. Does that work? Any questions? Okay, so again, we're going to make the right shape. So I'm going to go, let's see, I'm going to put 2 pi thirds here. That's one cycle. This is going to be 0. Well, if I mark the middle, what's in the middle of 0 and 2 pi thirds? Pi thirds. What's in the middle of 0 and pi thirds?
Pi 6.
Pi 6. And why is that nice on this problem here? Because that's how far we have to move it. If this scale doesn't match up with the phase shift, it becomes a bit of a pain in the butt. Okay? Then you got to do a bunch of fraction arithmetic. Okay? Now, where is this? It is. It's at pi halves. Okay? Because I'd have, count this way with me. 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6. If you think of them all in terms of 6, it's a lot easier to compute. Any questions? Okay, where does it start?
0.
0, and which way does it go? Goes down how far? Goes down a half. Okay, so let's see, let's think about this for a second. If we're going to move down 1, yeah, we'd have room to do this. What if we did this? What if we said this is negative 0.5, this is negative 1, and this is negative 1.5? Is that all right? Positive 0.5? We'd still have enough room to move this down. So it's going to start here. It's going to go down to negative 0.5, back to 0, up to 0.5, and like this. So here are the points that I need to move. If you need to label those, please do. If you need to move it in stages, please do. Now, is everybody okay on this one if I move this to the right pi 6 and down 1 all at the same time? Okay, what am I going to do before I start moving anything? Since I have to move everything down 1, I'm going to draw a new center line. It's going to make a much better graph. So, there's my new center line. And if I need to go on the other side, I will. I'm going to take every one of those points, and luckily, my phase shift is pi 6, and my scale is pi 6. So I'm going to take this, I'm going to move it over pi 6 and down 1. Not one hatch mark, 1 unit, down to here. Over pi 6, down 1 unit. Over pi 6, down 1 unit. Notice that these 2 points that I moved that were on the center line are still on the center line. Do you see how that can be helpful in making the right shape? Over pi 6, down 1, over pi 6, and down 1. So here's the correct shape. This is the answer to this problem if it said graph it. Would you label it, please? Label those 5 key points. Again, if you can do this, you're in good shape for the test. Pi 6 comma negative 1. If we've scaled things right, this should be pi thirds, and I'm going to write negative 3/2 just because I really like fractions. Okay, this is going to be pi halves comma negative 1. Notice how all three of those that are on the center line will have the same y coordinate, so I'm going to do this one right now. By the way, if I was at 2 pi thirds and I add pi 6 to that, best way to think of this is in 6, 4 pi 6 plus another pi 6, so this is going to be 5 pi 6. And this one is at 2 pi thirds comma negative 1/2. So if you can graph that accurately, label all the points, then you're in good shape for the test. Are there any questions? Is this pretty easy? Okay, a little bit more vocabulary, and then we'll be done with this one. It says, find the number, let's see. So frequency. Has anybody in here had physics? A couple of you? Heard of frequency? Okay. So frequency is the number of cycles per unit of time. For example, don't recommend this, but if you were to stick your finger in one of these outlets, it's AC. It's alternating current. It alternates. It changes polarity 60 times every second. Okay? So how many times does it change per second? 60. That's the frequency. Okay? And per seconds is usually measured. We could just have a special name for that. That's called hertz. Okay? Now, there's a really simple formula for this to figure out the frequency. Frequency is 1 over the period. It's that simple. Please get this memorized. Frequency is 1 over the period. Well, what that means is the period is also 1 over the frequency. In other words, these two are reciprocals of each other. So if you know the frequency, flip it over, you've got the period. If you know the period, flip it over, you've got the frequency. Okay, so it says find the frequency of this right here. All right, well, let's see. If you want to find the frequency, it helps to know the period. So the period on this one would be, what's the normal period? 2 pi divided by 300. So the period is pi over 150. Okay, that is the period. If you want the frequency, you take 1 and you divide it by the period. So that would be 1 over pi over 150. Or what am I going to do to simplify this? Times it by 150 over pi. So the answer is going to be 150 over pi. What's the relationship between the two of these? If this is the period, what's this? The frequency. And what's the relationship? They're reciprocals. So if you, again, like I was just saying, if you know the period, flip it over and you've got the frequency. It's literally that simple. Okay? Any questions? All right. Last one. You've got a problem like this on your assignment. It says f of x is sine of x, g of x is x minus pi fourths, and h of x is 3x. Find h of f of g of x. First of all, can somebody tell me what it is when we plug one function into another? Very good. I heard it over here. What is it, David?
Composite.
They're called composite functions. What function do you start with? Start with g. What do you plug it into first? X. So I'm going to take this, start with g, plug it into f. You with me? That means it goes right here. So that's going to be the sine of x minus pi fourths. What do I take those things and plug them into? Plug them into h. So I'm literally going to take this, and wherever there's an x, I'm going to plug it in. So the answer on this problem is 3 times what? 3 times the sine of x minus pi fourths. That's your answer on that one. You have some problems like that. Okay? Think about the ones with frequency. They're not that hard. Okay, See you on Wednesday.